Yes. So in our last class, we have discussed about PN junction in reverse bias, as well as we have also started our discussion on PN junction, what happens to this PN junction when it is in the forward bias, right? So while discussing this PN junction in forward bias, we have discussed that, say, this yellow region, right? This yellow region was the depletion region earlier. Earlier means when in the no bias has been applied, right? This was the depletion layer width. Now, in that case, or maybe I should probably use the same color that we are using for this, right? So when the depletion was this, depletion region width was this much, we almost have applied no bias, right? We have not applied any bias to this PN junction. And at that time, we have a built-in electric field due to the built-in potential, right? That was EBI, right? Now, after that, we have forward bias this PN junction. So during forward bias, we have connected the positive terminal of the battery with the P side and the negative terminal of the battery with the N side. That makes this PN junction forward bias, right? And as a result, we know that the depletion layer width will reduce. So it has now reduced, right? We can see it this by this green one, right? So depletion layer width has reduced, right? And also, if we see from this the potential that we have applied, so here this is the applied voltage, this is the positive and this is the negative. So as a result, there will be an additional electric field or the external electric field due to this applied bias. So its direction would be this in this way, right? Opposite to that of the built-in electric field. So as a result, the resultant electric field would be given by this one, right? EBI minus E external, where this EBI, that is the built-in electric field, would be always much greater, always greater than this external electric field, right? That also we have discussed in the last class. So now you see what was happening due to this. Earlier, you consider when no bias was applied, so this was the total depletion layer width, and at that time this EBI was the electric field, right? EBI, or you can also say this EBI was the electric field and VBI was the built-in potential barrier, right? And this VBI, due to this VBI, the diffusion of holes from P side to N side and the diffusion of electrons from N side to P side was like it was balanced, right? Means there was no further diffusion of holes from this P side to N side and no further diffusion of electrons from N side to P side, right? But now you can see, as when you have applied the forward bias, this one, the resultant electric field has reduced, right? So the resultant electric field, when this electric field was reduced, now it is easy to understand, then that force is not there, which was earlier preventing the further diffusion of electrons and holes, right? So as that force is not there, so these holes can now diffuse from this P side to N side and these electrons from this N side to P side, right? Okay. If you have understood this, then you see this in this P side, right? There was a huge amount of holes, right? Means the hole is the majority carrier and the total number of holes would be equal to the Na, right? The acceptor concentration present in this P side. So that is quite large. And we can say, like, from here, that this is our depletion layer width, right? This is the depletion layer width once we have applied the forward bias, right? Now see what is happening from here. The holes which is the majority carrier in this p-type semiconductor, they will try to diffuse out, and when they reach to this N side, so again remember, this is N side, this is the P side, same as this, these holes, when they diffuse from this P side to this N side, and when they come to this N side, they will become the minority carrier, right? Because here the electron is the majority carrier, right? So this, when the holes will be coming here, they will say, like, hole concentration. Earlier the at equilibrium, the hole concentration was given by this Pn naught, right? But now this diffusion, a huge amount of hole is coming from this P side to N side, and say the concentration is this. Right, say the concentration is this. So here this is the concentration in this, right? And here is this X, the distance, right? So this is the concentration, right? Similarly, you can say, if you take this red one, this for electrons, the electron concentration will also be higher now due to this movement of electron, right? Electrons will also move from this side to this side. due to diffusions. So electron concentration in this side will also increase. So you can see at equilibrium, the value was, when no bias was applied, the value was, electron concentration was Pn naught, which was the minority carrier, right? But the electron now concentration has increased a lot, right? But what will happen? You see that now holes has come here. Okay, okay, if you consider from holes point of view, then let us finish the hole, then we will come to electron. These holes, when they have come here, they will see that we were the minority carrier here, but at the same time, our concentration is much higher at this point compared to this Pn naught. But we have, compared to this, maybe a higher concentration of electron here, right? Higher concentration of, say, this is the total value of Nd, right? The electron concentration. So these holes will now recombine, okay, with these electrons in this side. Now, as you are going far from this depletion layer edge, that concentration will further reduce and reduce. And if you do it bit more, if you know the semiconductor physics, then this decay would be actually a type of exponential decay. So this decay would be an exponential decay. So hole concentration would be maximum at this depletion layer edge, and as we go inside of this neutral N region, that depletion, that electron concentration or the hole concentration would gradually reduce, actually basically reduce in an exponential fashion, right? E to the power minus x, that fashion. Similarly, this electron whose concentration is much higher in this side, so when they will go to this side, this in the reach to this, when you go further and further to the neutral p side, their concentration will also gradually reduce, and that reduction would look something like that in the same exponential fashion, right? So this is the excess electrons. Why are we calling excess? Because the electron concentration is expected to be Pn naught. So these are the higher, which is, but here the electron concentration is higher than that. So these are the excess amount of electron that has come from this side, that has come due to the diffusion, and which is resultant due to the lowering of this barrier, right? Or the lowering of the electric field present in the depletion region. Similarly, these are the excess holes, right? Okay. Now, the question is, what would be the concentration here or here? What will be the concentration of electron and holes, okay, in this point? Right, after that it will fall exponentially, that we have discussed. But what will be the concentration here? Is it dependent on this applied Vf? The answer is yes. This value is dependent on this Vf. The more the Vf, you know, the lower would be this value, right? Or the lower would be the electric field. So the more and more will be the diffusion, right? Because this electric field only prevent the diffusion. So as we are lowering the electric field, more and more would be the diffusion, right? So as the diffusion is keep on increasing, with increase in this positive, with increase in this forward bias, so you can guess. So if you have a higher Vf, so obviously this value would increase probably from here to here, right? And this value will also increase similarly from here to here. Now, what would be this relation, and how much this would be increased, or what is the dependence of this concentration on this Vf? Again, it can be shown that this dependence is again exponential, right? Means what will be the value of this, that is dependent on the exponentially on this bias, on this applied Vf, right? So I hope now it is clear to you, right? This potential means how this potential can influence the concentration of excess holes and excess electrons at the edge of this depletion layer, right? Okay. Now you see that, you see, either you consider this excess electron or holes. Maybe let us consider this excess holes, right? So this excess hole in this N side, you see that there is a gradient, right? Or there is a concentration gradient of excess hole in this region. So again, and this gradient will be maintained. And at equilibrium, this gradient would be maintained. It only depends on what will be the gradient, because if you change this Vf, this gradient will start from like maybe from here. That might change because that is dependent on this Vf as discussed. But this gradient would be exponential, okay? And due to the exponential gradient, another current will flow. You know, there is a diffusion process by which the current can flow. So due to diffusion, these holes will try to move from this side to this side, right? And that will again create another current, which is due to the hole diffusion current. And you see, the whole diffusion current would be also, if I write, suppose IH to represent this, the whole component of the current. So that is like this, right, in this direction. Now, if you consider this electron, the electron also maintains this concentration gradient. So in this neutral p region, so here also you will have an electron flow. So electron will try to move from this side to this side, higher to lower concentration. As a result, there will be a current which will be in this direction, right, opposite to that of this flow of electron. So here we can write it, suppose IN. So you can see this both IN and this both IH, they are in the same direction, and that IN like a and this IN and this IH will constitute the overall current of this PN junction, right? Is this basic part is clear to you, like how this PN junction current, I mean how a current can flow in a PN junction?
Excuse me, sir. Sir, the holes are excess holes or excess electrons concentration should be same on the edges.
It is actually good. That is a good question, but actually it is it might be same. It can be also different. This concentration depends, as I mentioned, this depends on this VF. This depends on this VF. At the same time, it also depends the value of NA and ND. Okay. For example, if this ND is much, for example, if this ND is much higher than this NA, right, then the excess electron concentration at this edge would be also much higher than the excess hole concentration here. Is that answer your question?
Yes, sir.
Okay, so for this, let me also put it here. This would be the excess electron and this would be the excess hole. Fine. So this would be the concentration of excess electron and this will be concentration of excess hole. So,
excuse me, sir. So one doubt, sir. Sir,
yeah, please.
The built-in electric field was caused due to the diffusion of the holes and electrons.
Right.
It is right. But if we have applied an external electric field and then we start the diffusion of the holes and electrons again, then I think that there will be a saturation point where the built-in electric field will gradually increase because the diffusion is starting again. So there will be a saturation point.
There would be a saturation point. You are thinking that even if we apply this VF, there will be a saturation point. Actually, there would be I will not say it is a saturation point, but I will say that it will reach an equilibrium point. Okay, where again this, due to that equilibrium, this depletion layer width or this total electric field, that will reach to its equilibrium, means that value will not change any further. Because I think what you are getting confused is that, maybe we can go to this. See here. So here earlier you have holes, right? This hole now have to diffuse out, right? Like this holes is coming from here, this side to this side, and this electrons which were here, and that would come to and from this side to this side. Okay, right? And so as a result, this part will be left, right? This region will be only left uncovered. So as a result, you will have a depletion layer or the space charge region, right? This part, you have the space charge region, this side, right? And here we have mentioned about the equilibrium point, because once a point will be reached when you have how much, actually the equilibrium is bit type of different. I think we have tried to bit simplified it. See what will happen after that. So once this equilibrium has been reached, there will be still diffusion process will still continue. How? See this. This hole will again, due to this concentration gradient, will try to move from this side to this side. It will definitely, nobody can stop it, right? This electron will also try to move from this region to this region. Nobody can stop this movement of electron. But at the same time, okay, there will be some minority electrons also, right, in this p side. right? And which are will be close to near to this, this depletion layer edge, right? Those electrons will see a force, which is electric field, like due to this electric field is this. So you know the electron, if you see this electric field, this electron will be dragged again back to this region, right? Similarly, some holes which are present in this region due to this electric field, that will be now dragged back to this P region. So actually there will be a drift and diffusion process that will be going on simultaneously, and there will be an equilibrium point when the rate of diffusion and drift, they will be balancing each other. You understand? So this will be when we have not applied any bias, but when we have applied any bias, so for example, in reverse bias, we have seen there is almost no current except the leakage current. But in forward bias, you have applied on VF, which by applying a constant voltage VF, we have made this VBI minus this resultant electric field here in the depletion region lower than the equilibrium value. As a result, the hole and electron, okay, will keep on moving. For example, you can consider a type of, this barrier as a barrier of a dam, right? If you reduce the height of the barrier of that height of the dam, then what will happen? This electrons, if you say the water are electrons, then electron will flow from this higher side to the lower side, right? And it will keep on flowing, right? It will keep on flowing as long as the barrier is low and as long as there is a supply of water. So here the supply of water is generated by this applied voltage source, right? And the barrier lowering is done due to the lowering of this EBI minus the resultant electric field or the resultant built-in potential near to this PN junction. Is that answer your question?
Yes, sir.
Sir,
Hmm.
sir, in the total sum of concentration of electrons in P N diode is constant, right, sir?
Could you please repeat total concentration? Can you please be more specific? In which region you are saying that?
Sir, I mean to say that in P region, the major charge carriers are holes and minor are electrons. And in
Right,
N region, the major are electrons and minors are holes, right?
right.
So by taking these PN junction into consideration, so the
Mm-hmm.
total sum of electrons in both PN junction is constant.
Mm-hmm. Right, right.
So sir, this, I mean, how the peak of this
Excess
concentration
electron.
is
So you were saying like then if their excess electron concentration is here, then what would be the concentration of hole here, right?
no sir, I mean to say
Then
that how this excess of electron is
uh,
dependent on the VF.
how this dependent on this VF.
Yes sir.
Okay. So how this is dependent on VF? Okay, you can think it of again from this way, right? Okay. Maybe I can put it maybe in this way. Say you have this lots of holes here, right? Right, say lots of holes here, and you have electrons on this side, right? And this is a say like this is a gate, and you have a valve here. So you can pull this valve up, and you can actually pull it a bit off and make a small gap here. You understand? And then what will happen if you apply a small voltage? Then maybe probably say like you have pulled this one little bit up, and this much you have a gap. So some electrons through this gap can move from this side to this side, some holes can move from this side to this side. Now you have pulled it little bit more, right? Then probably say now you have a little bit more, right? So you have more flow of holes from this side to this side, more flow of electrons from this side to this side, right? So if you further increase, if you further pull it up, then you have or basically you are creating more and more path for the electron and the hole to move from one side to the other side. Now to answer your question, here what you are doing with almost the same analogy, by applying this VF, okay, you are reducing this VBI which was present and preventing the further diffusion of holes and electrons from one side to the other side, right? Now as you are decreasing this VBI, how you are decreasing this VBI? By applying this VF. So higher will be the VF, the lower would be the built-in the potential barrier. Or you can create in this analogy, you can think of you are opening the gate more and more by lowering the barrier. So further and further, these holes can move from this side and electrons can move from this to this side. So as a result, as this more electron can flow from now this n side to p side, so more will be the concentration, right? As this more holes can flow from this side to this side, more will be the hole concentration on this side. Is that answer your question?
Yes, sir. Thank you, sir.
Okay, welcome. So here,
So the IM and IH mentioned, they are drift.
could you please IN and IH means?
IM. So in the
IN
concentration diagram.
here. This
Yes,
one
sir.
you were referring? IN, huh?
Yes, sir. And the IH on the other side.
IH on the other side.
So these are the drift currents. The
No,
currents formed
no,
in
no,
the
no.
drift of
These are actually the diffusion currents. Because you can see there is a concentration gradient, right? You remember in in this way that for drift the electric field have to be present, right? Right. And for diffusion, concentration gradient have to be present. Now you say you think in this way in the first class in the last class only we have discussed, right, that for a PN junction when you apply any voltage, most of the voltage will be dropped only across the depletion region. So in that point, from that point of view, you can think of that electric field only exists in the depletion region. So only inside this depletion region electric field exists. No electric field, almost no electric field outside in the neutral region. So if there is almost no electric field, then how? Then there is no question of this whole diffusion, whole drift current there, right? So it would be due to the diffusion only, right? And one more thing you see also from this, the electric field direction is, the resultant electric field direction is still from this N side to P side, right? And inside this depletion region, right? And hole, this move towards the in the same direction of this electric field. So hole cannot actually move if it is has to be due to drift, then the hole should move in this direction, right? Not in this direction.
Yes, sir. Sorry, sir.
No issue.
Thank you,
Okay.
Sir?
Well,
Sir, is it correct to say that the depletion region will increase a bit slowly, like as time proceeds?
depletion region will depletion width of the depletion region will increase slowly.
Like because as the diffusion is happening, so the amount of ions minus, like initially this depletion region was formed due to the diffusion only. No, sir.
See, as long as you have not changed this VF, right, your depletion region width will remain constant. When you change this VF, then only there will be a question of changing this depletion layer width. As long as you have kept this VF constant, there is no change. Okay, not even due to the diffusion. This diffusion is happening because you have lowered the barrier potential or this lowered the electric field, right? And this electric field this will be maintained by this VF only. Okay, this will not be affected due to this diffusion process, further diffusion process. Fine. Okay, so here, if you have understood this, like at least the basics of this, how does the current flow in a PN junction in forward bias, right? Then it can be further shown that this ID, the resultant diode current that will be flowing in the forward bias, that can be given, obviously not only in the forward bias, obviously this equation is also valid in the reverse bias, this IES into exponential of VD by eta Vt minus 1. So let us see this equation. So this is called the diode current model. So in semiconductor, this model means a mathematical equation which describes primarily the current voltage characteristics of a device. Okay. So we have seen this PN junction. Now we are saying that the PN junction I and V, current and voltage, are related by this equation. So what does this equation says? To discuss it, maybe I can draw it like this: Pn and you have a voltage source of VD which you have applied this, right? And the current which is flowing is ID. Then if we apply across this PN junction amount of voltage VD, then then a current will flow if this PN junction is in forward bias, and this current would be given by these expressions. Now here in this expression, you see which are the terms that are known to you. For example, this VD, right? VD is this voltage. This ID is this current. VT, we have already discussed. VT is the thermal voltage at room temperature. Its value is 26 millivolt, and this VT is also, we know, this can be represented by this KT by Q, right? We have already done this, right? This one is constant, and now what is this eta? The eta might be new to you. This eta is the ideality factor. Or emission coefficient. Okay. Now maybe we'll discuss about this later, about this eta a bit more after a few minutes. Now what is IS? IS is the reverse bias saturation current. Right, reverse bias saturation current, and its value would be in the range of say 10 to the power minus 13 amps to maybe 10 to the power minus 9 amps. Okay, it can vary. So you can see that value of IS is pretty low, 10 to the power minus 13 to 10 to the power minus 9, but still this value of IS significantly influence the amount of current that will flow in a particular PN junction, because here you can see from this IS has been multiplied with this exponential term which is VD by eta VT. So maybe we'll come to this how this means what will be the approximate value of this function and how this can influence this ID maybe in the next page. So I hope from here this equation part is clear to you. And regarding this ideality factor or this emission coefficient, it determines how ideal a PN junction is. Okay. So in certain cases or in certain PN junction, you will find that ideality factor would be considered as 1, right? In certain cases, you will also find that ideality factor would be higher than 1, right? So overall, you can say this ideality factor would be in between 1 to 2. Okay, ideality factor lies between 1 to 2. It's for your understanding, this much is enough, but you know, in some places we have also seen ideality factor which is actually higher than 2, but that, yeah, that is fine, right? And if nothing has been mentioned about ideality factor, then you can consider ideality factor equal to 1, right? If nothing has been mentioned about his ideality factor. So you can say in that case, the equation would become quite a bit easier. That is ID equal to IS exponential of VD by VD minus 1. Right. Now what this ideality factor also depends on the region of operation of a particular PN junction. Maybe that I can show you in the next page.
Excuse me, sir.
Huh.
So this equation is valid for both reverse as well as forward bias.
Yes, exactly. This is valid for both forward and reverse bias.
Okay.
Okay, exactly the same thing we will now see it here. Okay. So let us write the current equation once again. So we have seen this current equation is ID equal to IS into exponential of VD by eta VT minus 1, right? So here we are trying to plot it, the current voltage characteristics, but we know that mathematically that diode current voltage characteristics can be represented by this equation. Okay, and let us try to plot this equation here. Okay, so here we will try to plot the same equation in two different ways. In first case, so you can see the y-axis is log. The y-axis represents this current only, ID in amps, and it is in log. So you can see that 10 to the power minus 12, 10 to the minus 13, minus 8, 10 to the power minus 6, right? Whereas in the other case, we have plotted it in a linear scale. Like you can see this 1, 2, up to 6, this milliamps. Like, so it is linear, is a log. And here, this VD is, obviously VD generally we always plot in the linear scale only. So it is from 0 to this 0.7 here, right? We are not plotting intentionally in the reverse bias direction. I will mention why not. So here in a linear scale, we have trying to plot it both in the forward bias. So you can see from 0 to up to 1 volt VD. And in the reverse bias, we also try to plot here it restricts due to space. I have only plotted up to 0.6, but it can go up to much higher value. Okay, so let us try to plot it. And for here, let us say that eta value is equal to 1 and this IS value is equal to 10 to the power minus 13 amps. Now I need and help from you. Please guide me where in, or say 10 to the power minus 12, say, then it would be easier. Please guide me. How should I plot? Okay, what would be the value of ID at VD equal to 0?
0.
0? Oh no. Please see that you put VD equal to 0.
Yes.
You put
Sir, 1 minus
VD
1
equal to 0, then
0
what will
only,
happen?
0 only. 0.
Is 0
Sir,
only,
0.
right? Because you put VD equal to 0, then it will be like 0 means basically 1 minus 1, so it will be 0, right? So it is expected, right? When you have not applied any voltage across a PN junction, then there is no question of current, right? So the current is expected to be 0, right? So now say we have not increased this VD a lot, but we have say the VD is like this much, VD equal to 0.001 volt. So now, can you give me some idea what would be the value of current?
Sir, 0.001 times IS.
0.001 times. Okay, maybe let us not even go to that too much detail because that is, yeah. So anyway, so suppose now we are increasing from VD equal to from 0 and we are moving to increasing this VD little bit towards in the higher side, right? So maybe we can assume like, if this is close to this 10 to the power this 10 to the power minus 12, then when you approach this suppose a little bit higher value, then it will be higher than 10 to the power minus 12, right? That we can expect, say here. So let us not make the situation a bit more complicated. Let's say it will be higher than 10 to the minus 12, right? Then after that, how it will increase? Sorry?
There should be an exponential increase.
Exponential increase, right? But this scale is in? This is in?
The logarithmic scale, so the
Logarithmic.
graph will be
So
linear.
it would be linear, right? So it would be linear, right? So say like it will increase like this, right? So this is what this expression is saying us, right? That it would increase logarithmic, it is increased exponentially, and as this is a log scale, right? So it will be a straight line in log scale, right? Okay. Now remember, still we have considered eta value is equal to 1. We will come back to the eta value a bit later. Okay. Now the same expression, now we are plotting in the, okay, in a linear scale.
Sir, it has to start from 0, no, sir.
It has to start from 0, but in log scale, do we have a position of 0?
No, sir. Yes, I got it.
Yeah, right. Yes. Right. Okay. So here, this in ID. So where from, please guide me while I want to draw this ID, this equation here. So how it would look like? At 0, value is 0. Then it will increase, right?
Exponential graph, sir.
Exponential graph, right? And maybe most of you are familiar with this plot, right? And it will probably look. Do you agree with me?
Yes, sir.
Okay, so here you can see up to a certain voltage, it seems in a linear scale the current is actually negligible, or you can say that close to zero, right? It appears to be, but after a point the current will increase type of almost in a perpendicular way, right? But if you see in the log scale, that's what I have drawn this two side, this like up and down, so that you can see it. So here you can see even, so here from here it appears like below 0.6, the current is 0. But if you see from here, this is below 0.6, the below 0.6, the current still exists. So current is never 0, right? Even though it appears to be 0 from the linear scale. Right? Okay. Now, tell me what would be the value of current in the reverse bias from this equation?
Negative.
Obviously negative, but give me the value.
Sir,
Huh.
sir, which factor in that equation distinguishes it from reverse bias and forward bias?
Yes,
There
it
should be some.
is the VD only, right? It is the VD only, no? This potential. This VD.
Sir, like is IS same for both reverse bias and forward bias in
Yes.
the
Yes. Yes.
Is eta same in both these reverse bias and forward bias?
Yes.
So
This
then
expression, this expression is valid in both forward as well as in the reverse bias.
Yes, sir. But sir, direction of VD is changed now, sir. It's become negative.
Yes, direction of VD, you are right, direction of VD can change, it can alter, it can be reversed, but that's what I'm saying. This equation represents the diode current equation in both bias. Okay, so it does not mean that in reverse bias, this IS will change. That is okay. You will understand. Just give me a minute. You will understand it. Okay, just give me a minute. See, here, what is the beauty of this equation? At reverse bias, say eta equal to this eta value is equal to say 0, sorry, 1, right? Then there is no eta. Then you see what is this equation is saying us? It's saying IS into exponential of, say this VD value is now reverse bias. Now we have reverse bias VD value is say 0.1, right? And this eta value, this is 0.026, this minus 1. Yeah. Could you please check this value? Exponential of minus 1 by 0.026. Yeah, please check it quickly. We have to.
It is minus 1.
It is?
Minus 1.
Minus, which one is minus 1? The total thing is minus 1, you are saying? Or only the exponential one is minus?
The exponential part minus.
Yeah, the exponential part become minus 1. Are you sure?
The exponential part is approximately 0.
Okay, let me put it in this way. Give me the value of this ID. Give me the value of this ID in terms of IS.
Sir, minus 0.97. Yes.
Maybe can you please say one by one? Otherwise.
So minus 0.97.
Minus 0.97.
No, sir. Minus 0.0038.
No, what are you saying? Just.
Sir, it's minus 0.98 IS.
Minus 0.98 IS. Okay. So then can you not, okay, this you have understood. Okay. Now you say this, what would be the value of this ID if I have changed it from exponential of say 0.5 by 0.026 minus 1. Now give me the value.
Uh, 7543 IS.
Sorry?
7543.5 IS.
Sorry, I made a small mistake here. I should put a minus sign, right? Because we are considering now the reverse bias case.
Sir,
So,
minus 0.9999.
Minus 0.9999 IS. So you can see from here, that's the beauty here, right? That in reverse bias, once you have crossed around like minus 0.1 volt, then after that, if you keep on increase this value of VD or the reverse bias voltage, you see this ID or the diode current and or this PN junction current will remain constant almost to this minus IS value. That's why it is called the reverse IS is called this reverse bias saturation current. And this reverse bias saturation current, okay, the entire this formulation, this ID equal to IS, this has been taken care of considering the reverse bias as well as in the forward bias, or in other words I can say this is valid both in reverse bias as well as in the forward bias. So if I have to
Sir, on increasing the voltage, the value of ID is becoming constant, sir. So,
yes.
sir, means and you have shown means increase in the ID.
Yeah, right. But here it is in which direction? Please consider that.
No, sir.
This is in the forward
graph,
bias. No, this is in the forward bias.
Yes, sir. Yes, sir. This I am agreeing, sir. In the second graph, sir.
Oh, in the second graph. This is also in forward bias.
Sir, this is in forward bias.
You see
Okay,
that.
okay. Yes, sir.
It is zero, na? We are increasing. We are increasing in the positive direction, so
It's
it is
in
forward
positive
bias.
direction. Yes, sir.
Right, it is in the forward bias, right? So in forward bias, so you can check it from here. You can check, right? If you apply the, if you put forward bias like 0.1 by eta Vt, this has an exponential value, right? Then after that, if you make it 0.5, then you will see that this value, the total thing exponential of this 0.5 by this will increase rapidly, right? So this is increasing exponentially. But in the reverse bias, you have to put a minus sign here, right? So as a result, if you further increase, keep on increase also, this value will remain constant, right? So if I have to plot the same thing here, then probably it will look in this in this way, right? So in the reverse bias, the current is constant, and that constant value is equal to this IS only. I should say minus IS only, because it has a negative value, right? Now, in some in some book, or maybe in your book also, this Niemann's book also, in some places you will also find the characteristics in linear scale is been drawn in this way. Okay, say in the forward bias it is like this, and in the reverse bias it is and in the reverse bias it is like this. Okay, so here you might get confused, right? That say here the current appears to be almost close to zero. Then you might think, then how come this in the reverse bias the current might be so large, right? Because this current, forward bias current, okay, always has to be higher than the reverse bias current, right? It has to be, right? So but here I think if you notice carefully, then you will find it that here these axes, they are plotting maybe in milliamps, whereas this means this forward bias axis, this axis, whereas the reverse current axis, right, this might be, they will be plotting in microamps. So that the author can show you how this IS will look like. This is minus of IS. You understand? Because here, if I both plot, suppose if I am plotting everything in milliamps, then in this milliamps, this nanoamps or this microamps, or maybe so, if it is not in microamps, it should be in a nanoamps. So if it is in microamps, then the value of nanoamps will be almost look like in zero. If the author want to show you that how this IS will look like in the reverse bias, then they will plot the forward bias axis in different scale and the reverse bias axis in different scale. Okay, and also here, like you understood that the reverse bias current would be constant. That is true, right? Reverse bias constant appears to be constant, like that is true, but that is only once you have crossed a certain value of reverse bias, right? For example, here we have, I have shown you this ID. When this ID value is, when this VD value is -1, then you see it is approaching towards this minus IS, right? But if you consider a value of suppose 0.05 volt minus this, then you will see that this ID is not equal to minus IS, but it is lower than that, right? And that is what you can show it. You can see it from here, that when this value is lower, right? VD value is lower, means lower than this 0.1 volt. You can see that this IS will also gradually gradually decrease and then reach to the value of minus IS, and that is also quite clear from this expression. It has to be, right? Okay, so now if you see these characteristics, right, this linear scale characteristics, then you will find that this particular this PN junction, these characteristics are they have type of rectifying characteristics, right? So in forward bias it can conduct current, and in the other direction it cannot conduct current. So it's this characteristic resemble to the diode, this characteristic resembles to the diode characteristics. If you recall, or if you have heard of this, earlier vacuum diodes, right? Earlier these solid state diodes were not available. At that time only vacuum diodes were available. So this characteristic resembles to similar to that of this diode. So as a result, these devices are also called this PN junction diodes. Okay, right. So here you can also see that this diode current will increase in the linear scale after a certain value of VD, right? And that particular voltage is called the cut-in voltage or turn-on voltage, right? And typically this value would be for silicon diode 0.6 to 0.7 volt. Right? Okay. Now, yeah, before we end this part, so we have also talked about this eta, ideality factor, right? Now, how this ideality factor play a role? See here. Which color should I pick? Maybe, yeah, maybe this one. Yeah, see, this ideality factor here we have considered 1, right? And for most of the PN junction diode, for moderate values of VD, you will find this eta value to be equal to 1. No issue in that. But as you decrease this VD, then you will find the characteristics would not follow this curve, but rather this characteristics would follow this type of path. Okay, then it will increase, like it will merge with this line and it will further increase. So here obviously you can say this eta value cannot be equal to 1, right? So here actually eta value is higher than 1. Okay, so that, right? So here this lower VD region, there is something called recombination current, and that plays a role, and as a result your characteristics would deviate from the ideal, from these equations. And to take care of these non-ideality things or non-ideality factors, this eta term or the non-ideality factor is actually been introduced in this diode current equations. Okay, so that is the whole significance of this eta term here in these expressions. Okay, yeah, here one more interesting thing maybe I should discuss. Just a minute before we go to the breakdown. Yeah, so you see from here, let me write this diode equations once again. So this ID equal to IS, this exponential of V D by Vt minus 1, right? Okay, now see, if this Vd value, okay, what is the value of Vt? It is 0.026 volt, right? Now this, if this Vd value is say if this VD is greater than 3 times of this VT, then this is exponential function, right? So it will be like then exponential of this 3. So compared to this term, you can probably neglect this -1 term, right? So if you neglect that, then this diode equation means the diode current equation is simply like this: Is exponential of Vd, and we are considering eta equal to 1 Vd by Vt, right? Only this much. Okay, right. Now say if we increase this Vd by, say, earlier, okay, how to say that? Say if I increase this Vd by this 60 millivolt. Okay, increase Vd by 60 millivolt. Then can you give comment that how much will be the change in ID? Please do it quickly. If I change Vd by 60 millivolt, what would be the change in ID?
Sir, 10 times.
10 times, right? So remember that it is 10 times. So have all of you understood? Guys, I am waiting for your reply. If you have not understood, please tell me.
Yes.
Right. Okay, if you have understood, good. Then please note down this thing. This is very important. See this also for the diode current. If you increase this Vd only by 60 millivolt, so you know how small this 60 millivolt is? 1 volt is equal to 1000 millivolt, right? 1 volt equal to 1000 millivolt. And if you are increasing this Vd only by the 60 millivolt, then you see that it causes a change in ID by 10 times. So ID increases by 10 times, one order, right? By only changing the value of 60 millivolt in this Vd, right? So you can understand from this or give get an idea that how much ID is dependent on this value of Vd.
Sir?
Huh.
Sir, isn't the increase in ID also depends on the value of Vd?
On the value of Vd?
Yes, sir.
Vd. That's what we are saying, na? Vd, if this Vd increases by 60 millivolt. So we are considering the increase in Vd only here.
Sir, I am talking, sir, it is delta Vd, right?
Delta, no, delta Vd means suppose earlier the Vd was 1.1 volt and now I have changed from this 0.1 volt. I have now made 1 volt Vd equal to 1 volt, 0.1 volt plus 60 millivolt.
Yes, sir. Sir, so it is delta Vd. I mean the change in Vd.
Right.
Sir,
okay.
It also depends, no?
It also
depends on Vd, right? Like if we are changing Vd from 1 to 1.06 or we are changing 2 to 2.06, then ID will change accordingly.
Right. So maybe you can see it from better from this point. Like you can see if you are considering like 0.3 as the reference, then if you are increasing it from 0.3 to 60 millivolt, then the change in current would be this much. Okay. So this diagram is not very perfect. So you can see from here it is not actually one order. So if you increase it by 60 millivolt, right, then the amount of increase in ID would be one order. Do you agree with me?
Yes, sir.
Okay, now you consider 0.4 volt, right? So here compared to 0.3, the current value is higher, right? But still from 0.4, if you change it by 60 millivolt, then again that increase or the increment in ID would be again one order only.
Okay, sir. Understood.
Okay. Just a minute. Let me just. Yeah. So yeah, maybe we will cover this and maybe then we will take a small break. Okay. So now see that this diode equation, maybe let us write this diode equation once again. ID equal to IS exponential of Vd by Vt, right, minus 1. Right. So here, let us also consider what will be the effect of temperature, right? What would be the effect of temperature on this diode characteristics, right? So again here, I have again plotted in log scale as well as this linear scale so that you can get a better feeling of these things, right? So what will happen actually if you increase the temperature, say from this T1 to T2, right? Then suppose for T1 the characteristics is like this. Okay, so here to make it a bit correct, so I should make a small gap here, right? It cannot add Vd equal to 0 because its value has to be 0, right? So at T equal to say T1, at T equal to T2, where this T2 is higher than this T1, right? Then you will have an increase in this current, or maybe the stroke. You will have an increase in this current. So I have to try to plot in parallel line with this T2.
Sir,
right?
Why increase, sir?
Why increase? Very good.
Okay. VD is yes, sir. Got it. Sorry, sir.
You got it? Okay, great. So,
yes, sir.
Right. Now say we further increase it T3. Right. Then for T3, it would increase like this. Right? Okay. Because here,
VT is KT by Q.
Right, KT by Q.
If we increase the temperature, then the value is increasing in denominator. So shouldn't it decrease?
That is a good question. But here we have not probably discussed what would be the dependence of IS, right? What would be the dependence of IS on this temperature, right?
Yes, sir.
Right. Okay. So it will be like T1, T2, T3, right? And if the same thing we have to plot, suppose in the linear scale, then yeah, the next color we have taken it as an T2. For T2 we have used this blue color, so we should take it as T2, and for T3 okay. Now here please remember one thing, that this reverse bias current or reverse saturation current, this IS, right, or maybe I will write it. This IS doubles for every 10 degrees centigrade rise in temperature. This IS, right? So as the temperature is increasing, then this IS value would increase actually quite drastically, and that will influence the effect, that will influence the total value of ID, because the whole thing, see, this thing is being multiplied by this total exponential term. Okay, so I would request you to please just think about it, even though there is an VT term here, and try to correlate why from this equation by changing, and if you know that IS should get double for every 10 degrees centigrade rise in temperature, then whether you are expecting this type of characteristics or some different characteristics. Okay, please do. Please keep a thought on this and please think. Okay, in your off time. I think you will finally agree with this plot. Okay, now here in this context, I would also like to maybe, but this is not that way is relevant, but maybe giving that, if I write that equation, it would be better. Just a minute. This is the equation of IS only. Okay, so here this is not important from the this from this course perspective, right? But just to give you an understanding how this IS is dependent. Right. So this is basically one simplified expression of this IS. So A is the area of the diode, Q is the charge, Dn you know, right? Diffusion coefficient, Ln you probably do not know. Ln is the diffusion length. We forget about it. What is most important here is this one. You know, you consider this one, that this IS is dependent on this Ni square. Here this IS is dependent on this Ni square, right? Remember that Ni square. And we have seen earlier that this Ni, right, Ni is exponentially dependent on this temperature, right? If you have increased this temperature a little bit, then this Ni will increase exponentially, and Is is dependent on this Ni square, right? So, and we have also seen that this for silicon Ni is 10 to the power 10 per centimeter cube at room temperature, right? For germanium, what was Ns? For germanium, what is Ni? You forgot.
2.4 into 10 to the power 13.
10 to the power, is it 10 to the power 13 or 16? How much? Germanium? Yes, you are right. 10 to the power 13. 2.4 10 to the power 13. So if this Ni is higher, right? If this Ni is higher, then Is is also expected to be higher.
Sir, but the formula for Ni is not directly proportional to exponential of t.
Right. Then how? Okay. What is the actual relation?
So you write it like b t raised to power 3 by 2.
Right.
Is
Right.
exponential of minus Eg by 2 kt.
Okay. So let me write that then. So it was Ni equal to b t to the power 3 by 2 into exponential minus Eg by 2 kt. Right?
Yes, sir.
So it is not easy. Is this Ni not exponentially dependent on the temperature? You forgot. I have also asked you to draw one plot of Ni versus temperature.
Yes, sir.
Yes. So how that plot was coming? That was
Exponential.
Exponential, right? So it is exponential, right? Yes, but from here, what I wanted to say is that, see, from here, that this Is is dependent on Ni square, right? And this Is and this Ni value would be different for different materials. For example, from silicon, if we move to germanium, which has a lower band gap, then its Ni is also higher, right? And higher Ns means higher would be the value of Is, right? Now, higher would be the Is, so that means what? Higher would be the leakage current, right? So, suppose for germanium, okay, or maybe we will again come back to the germanium, but before that, let us complete the silicon part only, then we will move to the germanium. So, this is in the forward bias, right? If suppose we want to plot it in nanoamps and we want to show the reverse bias current as well, then for T1, if this reverse bias current is suppose somewhat like this, right, then for T2, the reverse bias current would increase, right? For T3, it should further increase, right? This is for silicon. Again, remember that this is in milliamps and this is in nanoamps. That's why I can show it like this, right? Okay. Now, suppose instead of this is a silicon, right? So all these are silicon. So this is again, these are silicon, right? Suppose if we had that germanium one, right? So can anyone tell me how the germanium diode characteristics would look like here? Anybody? Anyone guess?
Above SI.
Sorry?
So the current will be higher than in SI.
Current would be higher than the silicon, right? So the reverse bias current would be higher, right? Like that. What about the forward bias current?
It will be, the rise will be before the T3.
The rise will be very good. The rise would be before that of this, right? Okay, but see here, first thing is that this cut-in voltage will be lower compared to that of silicon. You agree with that? Okay, fine. But what about this reverse bias, reverse saturation current or the leakage current? See, in the reverse bias, ideally we want there should be no current, right? There should be no current because this current is not doing any action, right? This current in the forward bias, we probably will see in the later half that it will do some work, but this current is completely wasted. So we want this current to be as low as possible. Now we can also see that with increase in temperature, this current will further increase. That is one of the reasons why first semiconductor was germanium. Okay, first semiconductor was germanium, but later on it was found that the germanium p-n junction becomes so leaky with increase in temperature that is almost not of any good use, right? So then people have thought of using move from germanium to silicon, right? So you can see in the total this that this concept from the perspective of these two different materials, like why there is a shift from germanium to silicon. That is one of the, obviously one of the reasons, but there are other reasons as well why for moving to the silicon, right? Now in this context, if I ask you, suppose instead of this silicon we understood germanium and silicon, but what about gallium arsenide? We can also make a compound semiconductor p-n junction. Then can anyone tell me how the characteristics of this gallium arsenide would look like in the same plot?
Sir, the cut-in voltage will be higher.
Very good. The cut-in voltage would be higher. Say I don't know what will be the cut-in voltage, right? Because it again depends on this voltage and this doping concentration, but it would be higher. Say like this. Okay, this is for gallium arsenide. Say like this. Just okay. What will be the reverse bias current? It should be. It is expected to be lower, right?
Yes.
Okay, so I think you at least get this basic idea, right? How these characteristics would look like at different temperatures and for different materials, right? Okay, now I think we can just take a small break, right? Water break, and come back in 2-3 minutes. Okay.
Sir.
Huh.
Sir, what is the log scale? I could not really understand. What is that log which you're writing there?
What is the log scale? Achha. Okay.
I mean, whose log is being taken?
No. Whose log is not taken? Okay. So, yeah. See. See, the value is means the way how to represent what is log scale. Have you means are you not familiar with this like log scale? Means I'm trying to guess like where from I should start explaining this. So have you gone? Have you come across this log scale before or no? Hello.
Sir, not really. I've come across, maybe I've come across, but I don't remember.
Okay. Fine. See, the thing is that in linear scale, okay, then only what will, whose log, you are right, whose log has been taken, we are not taking any log, but see, here, suppose if you are plotting something in the y-axis and its value, you are writing 1, 2, 3, 4, 5, and all this, right? Now, and say these are in like milliamps, right? So basically 10 to the power minus 3, 5 10 to the power minus 3, 4 10 to the power minus 3, 2 10 to the power minus 3, right? But suppose and with this we are getting a characteristics. I am trying to explain from the context of this diode characteristics only, right? You are getting a characteristic like this, right? And here, so if I say like what is the value of current at this voltage, so you can easily say like this would be the value of current. Then if I ask what is the value of current here, you will say like this is the value of current. But if I ask what is the value of current here at this voltage, then if you see it from here, it appears to be that like current is almost zero. Or if I only provide you this plot, you probably cannot say it clearly that this is the value of ID from this scale, right? But instead, if I suppose instead, suppose if I plot plot these characteristics like this, that this value is 10 to the power minus 12, this value is 10 to the power minus 10, this value is suppose 10 to the power minus 8, this value is 10 to the power minus 6, say like to take it a bit up, this value is 10 to the power minus 4, this value is 10 to the power minus 2, and then if I again suppose, okay, then what is happening here, see how we are presenting these values, okay, these are 10 to the power minus 12, 10 to the power minus 10, 10 to the power minus 6, 10 to the power minus 6, minus 4, minus 2. So these are, see, if you are changing from here to here, what is the change? Hello, can you hear me? So what is actually, I cannot see your name here. So what is your name? Could you please give me your name so that I can call you?
Swarup.
Sarup. Okay, Sarup. So what is the difference? What is the difference between here from here to here? 100, right?
It's becoming 100 times, yes.
100 times, right? 100 times. You were right. 100 times, right? From here to here, it is again becoming 100 times, right? From here to here, again it is becoming 100 times. From here to here, it is becoming 100 times. Again, from here to here, it is becoming 100 times, right? But if you see from here, the difference between these two is the difference now. Here is 1. This difference is 1. This difference is 1. This difference is 1. These are linear, right? But if you see there, this is 100 times. If you see from here, this is 100 times. If you see from here, this is 100 times. If you see from here, this is 100 times. If you see from here, this is 100 times. So it is changing a, in a type of that this fashion, in a this, what is you call that, in a GP fashion, right?
Yes,
so,
sir, it's getting multiplied.
Right, it's getting multiplied. So this is this scale is called the log scale representation.
Yes, I got it.
Got it. So this scale is called the log scale representation. So here, if you now plot the diode, the same thing here, then you would get a characteristics like this, right? Because here it is changing the difference is like the difference is 1, right? And here the change is by 100 times, right? So as this is a log scale representation, so this characteristics would be the linear one, right? And here you see for any voltage, even for like this voltage, which you probably cannot get what is the value of current here, but you can get from here like this is the value. At any point you can get the value. Is that clear?
Yes, it's clear.
Okay, then Swarup, just give me another 1 or 2 minutes. I'll just come back. Huh? Okay, so you see from here, now we are trying to give a bit more focus in the reverse bias. So again, we are plotting in linear scale here, the y-axis, the current, right? And this is the forward bias. So obviously this is a 0 volt, right? This is 0 volt. So this is forward bias. This side is reverse bias. And you know the characteristics so far what we have studied is will look like this. Right? So we are plotting in the same scale, right? We are not changing it, so it will look like this only, right? But and we know that this current would be now here constant, and the current would be equal to minus of Is. Can you hear me?
Yes, sir.
Okay. Yes, sir. Okay. So and this current is Is. But the thing is that, like as you can see from here, that in the forward bias, right? In the forward bias, once you cross this cut-in voltage, right? Cut-in voltage, which is represented by this symbol V gamma. So once you cross that, then the current will increase, right, drastically, like almost perpendicular, right? And you really cannot increase this diode voltage Vd more than this, because now after that, if you a small change, you know that after only 60 millivolt change will change the diode current by 10 times, right? So that basically will limit that Vd across means the applied voltage across the diode. But you really cannot change this Vd much after that once the diode has started conducting, right? So we can understand from here that the diode voltage in the forward bias is limited close to that of this V gamma of the cut-in voltage. But what about in the reverse bias? Then in reverse bias we have seen the diode current is only Is only, right? But then will it be Is for all the time, or or in other words, can we keep on actually increase this Vd in the reverse bias as like as per our wish? The answer is no, because after a certain value of Vd or reverse Vd, one breakdown phenomenon will occur, right? So this value is called the breakdown voltage, right? And the after that the current will increase drastically. After that the current will increase drastically. Now you can see here it is almost perpendicular, almost, but you can see still there is some like slope, right? But for during breakdown, the these characteristics would be almost like you can say it is very close to the perpendicular, right? It will be like current will increase very sharply, right? So that is called a diode breakdown. Now the thing is that why that breakdown thing is happening, right? So to explain it bit briefly, so what we can do is that we can again represent this diode in using this box symbol. So you know that this is a depletion region. So when the diode is in not been biased, you know there is an electric field which is from this, right? This will be the polarity of these charges, right? Immobile charges, and in this depletion region this would be the value of this electric field, right? Now when you have reverse bias this, so that means you have applied additionally this biasing. So as a result of this reverse bias, one external voltage has been applied, and we know that this external voltage it will be in the same direction of this built-in electric field. So we can write it as this VBI, there is a built-in electric field. Now this external electric field will be the same direction. That means the overall electric field is what? Overall electric field is this combination of these two, right? And you know that from our earlier discussion that this silicon and these two silicons which are side by side, they are actually bonded with covalent bonds, right? This bonded with covalent bonds. So basically these are basically electrons, right? These are covalent bonds. Now once this electric field once this electric field exceeds the breakdown electric field of the silicon, then what will happen? These electrons in this covalent bonds, okay, they will be they will be not be in this conduction band anymore. So they will suddenly go to this suddenly from this covalent bond, it will break and it will go to the conduction band and it will start flowing a current. And all this happens will be so quickly that at a certain moment, all of a sudden, you have a huge amount of holes and electrons, okay, generated at a certain point of time. Okay, and that results a huge amount of current and cause this breakdown. Now, what will be the value of this current? Okay, either this much or this much or this much. Yeah, that depends on the value of resistance that we add in the our circuit, right? So by using this resistance, we can actually limit this value of current, how much current should flow. So those things we will take in later on when we discuss analyze the Zener diode circuits. Okay, but as of now, you should understand like why breakdown should happen in a diode. Now, this breakdown voltage or this VB, this BV, this also depends on the doping concentration of these diodes. For example, this is NA and this is ND, right? So this breakdown voltage depends on this NA and ND as well. So for lightly doped or low doped PN junction or PN junction diode, the breakdown voltage is expected to be higher. This is lightly doped. Whereas if you dope this PN junction heavily, right? Dope this PN junction means if you have a higher value of ND, higher value of NA, then this breakdown voltage you can actually control BV1, say, right? So this is for high doping. Fine. So by controlling the this value of NA and ND, you can actually control the value of breakdown voltage, right? Okay. Now, this regarding this breakdown process, there are primarily there are two mechanisms by which this breakdown can occur. One of them is called the Avelian breakdown, and the other one is the Zener breakdown. Okay, so in avalanche breakdown, what will happen? So again, maybe I will draw this PN junction. So whatever is happening, it has to happen inside this PN junction, inside this depletion region only. Okay, so this is the depletion region, right? And you know this depletion region, there is an electric field, right? Okay, now when a carrier crossing, this and you have applied a reverse bias. So you have applied a reverse bias. When you apply reverse bias, so there will be leakage current, and due to leakage current, these carriers would be try to cross, this depletion layer. When these carriers are crossing this space charge region, these carriers gain sufficient energy, okay, from this electric field, because this electric field is now E built-in electric field plus E external electric field. So the electric field becomes so large that when the carriers are crossing, they gain sufficient energy, because what is like if the electric field is more, then the acquired velocity by these carriers would also be higher, right? So when the carriers have a higher velocity, okay, they can collide. You can think of like they can collide with the electrons in the covalent bonds while going through this depletion region and generate this electron hole pairs, means one electron and one hole. Now once one electron and one hole pair, so EHP, electron hole pair generation. So once this electron hole pair generates, they also try to move due to the presence of this electric field in opposite direction. They will again collide with the other covalent bonds, okay, and removing another electron hole pair. So okay, so like that, suppose one electron was moving, it generates one electron, one hole along with this initial electron, right? And it basically generates this two along with this in stage 2. Now this electron, while due to this electric field, will again generate one electron, one hole. right? So now in this stage, and maybe this electron again able to generate one electron, one hole, right? And this electron is again still here, right? This electron. And so like that you can see, like once this is suppose stage 1, this is stage 2, this is the stage 3. So as you like keep on thinking of this in this way, so you'll see that all of a sudden huge number of electron and hole pairs would be generated inside this depletion region, right? And you have an applied voltage, so you have lots of carrier all of a sudden inside that which will try to conduct. So you have an breakdown. Right. So this process is called, what is avalanche? You are familiar with avalanche in
Sir,
like,
I did not understand EHP generation. That means how collision will do this. I did not understand this process.
Okay. So silicon, they are bonded, right? You understand this symbol?
Yes, sir.
Okay, great. So now see, there is a free electron, and this free electron is moving, right? So this free electron can collide, say, with this electron, right? So once this electron is collide and it has sufficient energy, so to remove it from this covalent bond. So this electron is been removed. So this electron is now here, and once this electron has been removed from this place, so initially now it will basically give rise to a hole. It will basically give rise to a hole in this position, right? So you can see once this electron is colliding with electron in this covalent bond, it is generating one hole, one electron. So this is called the electron and hole pair, right? Electron and hole pair generation.
Sir, so this happens only for collision of electrons, right? Or not from the other side?
On the other side means?
Means from holes cannot do this electron hole pair generation.
I think it would be easier for you to explain from the point of view of electrons. Okay, because couple of things we have not discussed so far about semiconductor physics, and in this course probably we don't have that opportunity to go in that much detail. Okay.
Okay, sir. Okay, sir.
Okay, so try to consider it from the point of view of electron. Fine. So is this now electron hole pair generation clear to you?
Sir?
Yes.
And also there will be more electron hole pair generation due to the electric field, right? Not only a single pair that will be generated.
Not on, yeah. So that is how that is actually how the avalanche process is, right? One electron generating one electron. So still this electron is there, right? They can again collide, generate another two. This electron, generated electron, can create some more. So this is happening because of the electric field as well, you can say.
Even though there is no collisions due to the electric field itself, they all can form electron hole pairs, right?
Due to this electric field, yes. Due to the electric field, if the electric field is so high, that all the bonds can rupture at the same time, yes, it is possible. But beforehand only this avalanche process will occur because there is some leakage current, some electrons and some carriers are always flowing through the depletion layer.
Okay.
So whereas this Zener breakdown occurs due to the process called tunneling. So I don't know whether you are familiar with the word tunneling or not. Are you? Are you familiar with the word tunneling?
No, sir.
Okay. Okay, fine, no issue. So tunneling means when you have suppose one okay, how to explain it without explaining that physics. Okay, suppose you have a PN junction, okay, which is very heavily doped. So like for example, this is okay. We are familiar with the band diagram, right? EC and EV. Are you familiar with the band diagram?
Yes, sir.
Yes.
Yes.
Very good. Right. So when you have to draw the band diagram of P silicon, so it is EC EV. We are already familiar what is EC, what is EV. Then there is one more term that is called the Fermi energy level. Okay. So Fermi energy level is nothing like you can think of it is like that. Like for P type, the Fermi energy level would be very close to this EV. Like this is EF. Right, it is very close to. Now please do not ask about more details about Fermi level, but just take it in this way that for P type the Fermi level is very close to this valence band, and if you have to consider this N type silicon, then for N type silicon Fermi level would be very close to that of this EC. Okay.
Sir,
now
sir, your screen is freezed.
My screen is freezed. Okay. Could you please check?
No, sir. It's
proper.
No, sir, it's okay.
Oh, it's okay. All right. Maybe.
It's okay for me.
Okay. Maybe some network issue, right? Now, when you keep this to P and N silicon in contact, right? It will form the PN junction, right? And when the PN junction will form, and you have to draw it in terms of band diagram, then you should keep first this EF aligned. So when you keep this EF aligned, right, then EF is fixed, and then you have to draw this. So from P side, here it will be this EV, and here it will be this EC, and here you have this EC for N type, and you have this EV here, right? And you can like simply join like this. Right. So this is basically the band diagram for a PN junction. This is P side and this is N side.
Sir.
Huh.
Sir, could you explain it one more time because I lost my connection in between.
Okay. So are you familiar? Means could you please tell me from where I should explain? Means up to which part you are able to listen?
Sir, before the Fermi level.
Before the Fermi level. Okay, so you understand like this Fermi level EF for P type would be closer to this EV, and for N type Fermi level would be closer to this EC. Right. Now when you have to form a PN junction, this EF, this to EF has to first align. So this EF, when this aligned, right? So first you have to draw this EF is a single line. Then you have to draw this EC, right? EC and EV from P side and N side. Then you have to connect these two. So this is basically the energy band diagram of a PN junction diode. Here I think you remember that this axis is the energy axis. This axis is the distance, right? Distance along the PN junction. Now in a Zener diode, what will happen is that the band diagram would look something like this, bit more complicated. Okay. So here you can see, right, EC, EV, this is EC, this is EV. So you can understand this is P side, this is that N side. But what you can see from here, in addition to that, is this one, that here this EV, right? You know there are huge amount of holes, right? Huge amount of electrons, right, in the valence band that we have already discussed. So this valence band, huge amount of hole, huge amount of electrons, and here in this side, this EC, where the amount of electrons are bit less, right, compared to this valence band, because valence band you have a huge amount of electrons. And now you can see, if you reduce this gap between these two, this gap becomes so small, then you are basically approaching a situation, you are basically trying to separate like this huge amount of electrons with a region where the electrons are not that much large in numbers, right? So as a result, what will happen, these electrons from this valence band will directly go from here to here. This is called, you can think of this tunneling process. Okay, these electrons from here, they will tunnel, okay, through this barrier. Means it will say, you can think of it like that you have a like high pressure region here and you have a low pressure region here separated by a valve, and this valve is bit type of porous, okay, because it is so thin, okay, so that you can have an this from this high pressure, this side gas can actually move, go from this side to this side, right? So this process is called the tunneling process. So this Jenner breakdown happens due to the tunneling process, one thing. And the other thing is that for Jenner diode, the doping concentration has to be quite high. Doping concentration is very high, right? And you know that we have already discussed that when you make the doping concentration very high, then the breakdown voltage is expected to be reduced, right? So these Jenner diodes are made such that their doping such that their breakdown voltage lies in the range of say 5 to 12 volts. Okay, so this is the beauty of Jenner diodes. Jenner diodes are made to be operated in breakdown only. We will see it later on, okay, when we discuss this breakdown. So Jenner diodes are made to operate in the breakdown voltage only. Yes, please.
Sir, how we know that in the electrons in the valence band of p type are greater than the electrons in the conduction band of n type?
Because see, if you recall our discussion on this energy band gap, then we have seen, right, this Eg and Ev, this, like we have said that in the valence band you have all these covalent bonds, right? Remember, and you have huge amount of electrons. All the electrons which are in the covalent bond, they are actually the valence band electrons, right? And here EC is like only some of the electrons which can go from valence band after getting sufficient amount of energy and become free, and they become this free electron in the conduction band. So even if it is n type, right, the number of electrons here, free electrons here in this EC would be always lower than the number of electrons which are inside, actually you can say confined in this valence band in the p side. Okay.
Sir, even though that the doping concentration is very high.
Even though the doping concentration is very high. Yes.
Okay, sir.
So I had a question regarding avalanche breakdown.
Yeah.
So in the avalanche breakdown, most of the electron hole pair generations would happen in the depletion layer, right? Because it is the only region where we have the electric field.
Right.
So,
right.
So I think you told us that the depletion layer is not very large. It's in micrometers.
Right.
So the number of electron hole pairs which are even present in it would be finite. So
would be finite. Right.
After a particular amount of time, would the depletion layer not be would it not be have any more electron hole pairs to be generated, and after a particular amount of time we cannot get any current anymore because there are no more electron hole pairs to be generated?
No, actually, yeah, you understand. I think I get your question, but even though this region, this depletion region is quite thin, right? Like it also depends on the doping concentration, but this depletion region can generate sufficient amount of electrons and hole pair to cause the breakdown. Okay, to say it simply, it is like this, and yeah. And if you want to know a little bit more, then I can tell you a couple of things. Like you might be thinking this electrons, what is the probability that it will touch when it will it is like within this much region, how many collisions can happen. So it is not only like this, because whatever we have seen, the electron hasn't called a duped velocity, and these electrons movements are not actually like this type, right? Electrons will come here and go like that, straight line. It's not like that. It is rather this type of thing, electron movement. Like electrons will move like this, right? Like this, right? So if you see this instance and this instant final instance, then this electron has actually traveled more path, right, than this. So the finally we measure the velocity based on this straight line distance. But before that, electron has actually moved much more path, right? So that way you can see that the chances of collisions and all these things are much higher, right? So this depletion region can produce sufficient amount of electrons and holes to supply this amount of current. Okay, and right, and also you must also put it in this way. See, once this electron and hole pairs are being generated, they will they will take part in the conduction. But what will happen to this hole? Will it not be some electrons again type of filling this position? It should, right?
Okay, sir. Yes, sir.
Because you have not removed this, right? You have kept this battery right there. So this charge movement will always be there, no?
Yes, sir. Yes.
Okay.
Thank you, sir.
So, okay, I think
so, sir, if the temperature is higher, if the doping is higher, then Zener breakdown will occur before avalanche breakdown.
Yes, for Zener breakdown, we intentionally make the doping concentration so high that the mechanism of this breakdown is primarily due to the tunneling, and the breakdown voltage is usually between 5 to 12 volts depending on the design.
And sir, what is the range of avalanche voltage? I mean, breakdown voltage.
Avalanche breakdown voltage, in some cases, it may be more than 200, 300, even 1000. You can design. It also depends on the design, right? I am saying design, only one parameter we have discussed, that is the doping concentration. Other than that, the structure and all these things also determine what would be the breakdown voltage. Okay, but one of the primary thing is the doping concentration. So this PN junction diode whose symbol is this, right? And so if you see our previous representation, we are representing it like this, right? This is P, this is N. So in circuit, this is the circuit symbol, right? We present it like this. So this is that P side and this is that N side. And the polarity that we will assume, this is a plus, this is minus, and the flow of current is this. Because in the forward bias, current can only flow from P side to N side. In reverse bias, even though there is a small current, which is IS, but we will say that the diode can block the reverse bias current, right? Okay, then let us take a very simple circuit. Say that we have applied one sinusoidal voltage here, which is connected to this diode and connected with this resistance, right? So you can see that Vi, the input voltage, this is this, right? Sinusoidal voltage, right? Now this is V out. We are trying to plot this V out. Then we know that only during this positive half, this diode can conduct. You will get one current will flow through this, and that will result this V out. So as a result, V out, you will get a V out only this. But in the negative half cycle, the diode will behave as an open circuit, right? No current. So no current flow through this, no voltage drop. So you will get here 0 voltage. Right. Again, in the next positive half cycle, you will get this output. Here, no. Here, you will get this. Right. I think most of you are familiar with this. Right. That basically shows the rectification using diode. Right. Basically, this is very simple half-wave rectifier circuit. Right. But let us also think this phenomenon that instead of applying one sinusoidal signal, it is also possible that we can apply one this square wave, right? So here, instead of this, let us say that we are now applying this square wave. So when you are applying this square wave, so again, what will be the output, expected output? This expected output is quite, it should not be difficult to guess, right? only in this direction current will, current can flow, causing a drop across this V out. Here no conduction, here again conduction, here again no conduction, here again conduction, right? So it is expected like this would be like this, this, right? Isn't it? It is pretty straightforward. Now the question is, okay. Question is, if we consider a PN junction diode, I think in the last class itself we have seen that in this direction diode is in reverse bias, and we have seen in the reverse bias this expands, there is a prominent amount of depletion layer, right? You have a depletion layer capacitance. So one capacitance is always associated with a PN junction diode in the depletion region, right? And you know that the voltage across this any capacitor you cannot change instantaneously, right? You need some time to change this voltage across this across a capacitor. So if this PN junction in the depletion region it also has a capacitor, then also you cannot change the diode voltage instantaneously, right? Then what would be the effect of this capacitance in the diode characteristics? In most cases, like we neglect those things because our this time period of the signal is so high, means so large that these small transient things will neglect. But yeah, if you are really considering something, some waveform where this time period is not that high or not that large, then probably you should also consider the transient phenomenon due to this presence of capacitance in the PN junction diode. Okay, so for that, let us on briefly say a very simple circuit. Let us say that this diode, okay, this diode has been connected. There's a knob, right? There is a knob, right? You can actually connect it if required with this or with this, right? So when you apply throw this switch to here, it is basically connected with a battery which will forward bias this diode. And if you throw this to here, it is basically connect with a battery which will reverse bias this PN junction diode. And let's see what will happen. So let us say that initially we'll throw this, connect it with this, throw this switch to here. So now the diode is in forward bias, the current is conducting, and all these things are, whatever we have explained earlier, that is happening. And very easily what we can say from here, if this say this voltage is say VF, right? Then what would be the current again? And say this current is like ID, right? Then this ID would be equal to like VF minus VD by RF. So what is VD? VD is the voltage drop across this diode, right? VF minus VD by RF. It's pretty straightforward, right? Now, during this, what has also happened, that from P side, holes has actually injected from this P side to N side and electrons from N side to P side, and you have a distribution of holes like this, excess holes and excess electrons, right? Holes and these are electrons, right? Now you think the other situation. Now you all of a sudden you throw this switch from this position to this position, okay, which will reverse bias this. Now once you have connected with this reverse bias, then what is happening? Then see that you have already holes and electrons which are actually present in the neutral P region and the neutral N region. Now all of a sudden you cannot remove these holes and electrons, right? Because you can also think of it as this capacitance effect, right? Because of this capacitor, so it has stored some charges here, right? So it will take some time to remove these holes and electrons from this side to this side, from these holes from this side, this like when you now reverse bias it. So this is forward bias, right? Now you are going to reverse bias it. So when you reverse bias this is negative, this is positive, right? These holes has to come from this side to this side, and the electrons has to come from this side to this side, right? Because of this polarity. And it will take some time, okay, to take out these excess electrons and holes from their to their respective sides, okay. And that time is called this storage time, okay. And I will show you how that time is, means how it will look like actually. So maybe before that, when the diode is connected in this fashion, so can you tell me what would be the value of current? This is ID, right? So here, if this is VR, right? If this is VR, then what will be the current? Diode. If this ID was like this, right? But now the ID has to flow in the opposite way, right? Now because of the polarity, current has to flow in the other way. So it will be ID is basically the other direction. So it will put a minus of this VR by RR, right? So here in this plot, so here we have not shown anything in this, right? That is because we have actually this part is so small compared to the time period that we have neglected it. But suppose if we actually zoomed in this part, right? If we zoomed into this part, then this part will look something like this. Maybe, okay, one more before I go to that. Probably I will show you one more thing. That is this. I have 5 more minutes. Okay. So suppose if I have to plot this diode current ID, okay, here, then what will be the like waveform for this diode current? So you can clearly see diode will only conduct in the this positive half, this positive half, positive half. Reverse bias, there is no conduction, same as this output. So the diode waveform would be like this. Right, this is be the diode current waveform. Right, but if we really want to zoom in this region, this what is happening in this diode rear, then probably, or maybe not exactly this, but maybe in this region. Okay, we are zooming in. Then you see what is happening here. You have some forward bias current, right? All of a sudden the current, you have turned it off. So this turned it off, right? So this was the forward current, and this value of current is like IF, which is forward bias current is equal to this VF minus VD by RF, this one, right? This current, right? Now, when you have actually switch it from this on state to the off state, right, you will observe this, the diode will take an reverse swing, right, immediately. Then the diode current will be same for some time. After that, it will slowly go and reach to its that expected IS value. So this particular time is called the storage time. And this particular time is called the fall time. Okay, so you can see that once we are switching this voltage V in like this so sharply, the diode current cannot immediately going to 0, which we have shown here, right? But the diode, all of a sudden, you can see that diode will have an reverse bias current, which is given by this expression minus VR by RR, minus VR by RR. Okay, this amount of current will flow to this diode for a certain amount of time. That time is called the storage time. After that, that current will start gradually falling down and it will reach to this value, this minus IS value. Right. So if you were
so shouldn't the storage current also be above the x-axis? Like it takes time. It takes time to come to 0 only, but it is here you're sure that it is coming to negative side in no time.
So what I showed is that, yeah, right. Yeah, please, this also mentioned, I have here mentioned it. So you see that we are now plotting the current, right? We are now plotting the current, not the voltage, right? So these charges have to be removed, right? So once these charges has to be removed, so that will produce a current, immediate opposite current. Right. In the reverse bias, what you have shown that the diode will conduct no current. But here, what we can see that even in the reverse bias, for at least for a small amount of time, the diode will conduct a current whose value is this much. Okay. And after
So
that,
VD is 0 at that time. That
VD is
ID VR minus VD by RR.
VR minus. So which one you were talking about? This one or this one?
The later on.
Later on. Okay. Yeah. Please now say.
So sir, in the first one you are writing VF minus VD. But
Right.
in the second one you are not writing VR minus VD.
Right, because you see that, like, why we are not writing here, because in the first one we have this circuit, right? So what is the current? It is VF minus VD by RF, right? In the second half, what we are now writing, we are writing that, oh, we are saying why we are not writing VD here. Is that
yes,
your
sir.
question?
Yes sir, why we are not writing VD?
Why you are not writing VD? Then could you please tell me why you should write a VD?
Sir, because you are saying that instantaneously it will not go to 0.
Which one cannot go to 0? The diode voltage.
Yes sir.
Yeah, you are right. So I got your point. Yeah. Yes. So actually I should put one here, negative sign as well. You are right. There will be one this component as well, this VD component as well, because we should consider that it cannot immediately go to 0, right? So there will be one VD component as well. True. True.
Okay.
Right, but even you see that, then VR is much higher compared to that VD. It has to be, right? So its overall current will primarily be dominated by this VR only, right? So you understood that, when we are considering and type of case where the diode is switching from on to off, right? Then we should also take care of the transient part, which probably for your case, for your course is not that a big deal, but you should know that in the reverse bias also, for certain amount of time the diode will conduct. After that, the diode will stop conducting. But this is type of more transient phenomenon, not the steady state phenomenon. And for most of your circuit applications, we will assume in the reverse bias the instantaneously diode had stopped conducting. Right. So you don't have to consider this phenomenon. But for the sake of completeness, you should know this. Is that fine?
So then how does the voltage graph look like in the same situation if we zoom in?
If we same you zoom in, okay, that is a very good question. And could you please tell me how should it look like?
So it should gradually decrease to the 0 value, but it should not be instantaneous.
Yes, true. And eventually, what will happen, even when you are suppose changing it, when you are changing this voltage, suppose from this 0 to this value, right? The output voltage will also not change that way, very type of, straight line. But again, it will also change type of this, very with some slope. Okay, so all these things are there. So this is called the turn on transient. So earlier what we have discussed is the turn off transient, which is obviously much more important because of this storage time, and this is not very negligible. But yeah, you can probably neglect this part, turn on transient. But turn off transient in actual practical design, it is not negligible. Okay, if you have any question, otherwise, because it is already 10. Okay, then if you not have any other question, then thank you. So we'll meet again tomorrow.
Thank you.
Thank you.
Thank you, sir.
Thank you, sir.